Okay, so now welcome back, and we're now going to talk about, again, hypothesis testing and confidence interval construction. So let's first consider the slope. So in order to test the hypothesis that the slope is equal to some value, so we can hypothesize the slope is equal to anything. Usually people hypothesize that the slope is equal to 0. Because if the slope is equal to 0, that means that there's no association between the independent and dependent variable. So that's the typical null value. But it could be anything. I mean, it could be that you were reading the literature and you found that somebody found in the literature that the slope was something else, and so you want to see if it's true in your sample. But we're going to just say in general, we're going to hypothesize that the slope is equal to beta 1 under the null hypothesis, naught. Okay. And the test statistic is going to be a t-statistic where you take the value computed for the slope in your sample minus the hypothesized value. And again, normally this is going to be 0. Okay, so it's the calculated value of the slope minus the hypothesized value divided by the standard error of the slope, which is all of this. All this together, this whole thing is the standard error of the slope. I know that, by the way, because I told you that this formula, this says that the sampling distribution of the slope is normal, see, normal distribution. The first value before the comma sign is the mean of the distribution, and the value after the comma sign is the variance of the distribution. And remember, I don't know sigma squared, so I estimate it with the data. So that's why when I do this, this is the value that comes from estimating that variance from, well, this is the square root of the variance from the data. Instead of sigma squared y given x, which is sigma squared without a subscript, I use s squared y given x. If I don't know sigma squared x, I estimate that with sx, the s squared x. And so this is just the formula that I use for hypothesis testing for the slope. And this will be distributed as a t with n minus 2 degrees of freedom. Or we can set up confidence intervals for the slope by taking the slope plus and minus t times the standard error. Again, here I'm using the 97.5%. If alpha is 0.05, I would take 0.05 over 2 is 0.025. 1 minus 0.025 is 0.975. So it would be the 97.5 percentile of the t distribution with n minus 2 degrees of freedom. Okay, and then I multiply that times, again, the same expression, sy given x over sx, the square root of n minus 1. So in our example, let's say I wanted to test the hypothesis that beta 1 was equal to 0. That is, I'm hypothesizing that there's no association between x and y. And the alternative is that there is some association between x and y. So I compute the value of t, which is the computed slope, 0.97, minus 0, minus the value under the null hypothesis, divided by the square root of the variance of the slope. And so plugging in those numbers, I see that the value is 4.62. And I want to do a hypothesis test now where I'll reject the null hypothesis if t is greater than the 97.5 percentile of the t distribution with 28 degrees of freedom, or if t is less than the lower 2.5 percentile of the t distribution with 28 degrees of freedom. And so the critical values are 2.0484 and minus 2.0484. So anytime the value is above that or below that, I reject the null hypothesis. In fact, the value is 4.62, so it falls above 2.048. So we reject the null hypothesis at the 0.05 level. In fact, the p-value is exactly something less than 0.001. So this is if in fact the hypothesis is true that the slope is 0, this would be an exceedingly rare event. The p-value is very, very small. So this means that x provides significantly more information for predicting y than the naive model does. Now what's the naive model? The naive model is the model that says this is what I would predict the value of blood pressure would be if I didn't know anything about age. Okay, now if you didn't know anything about age, what would you predict the value of blood pressure would be? If you knew nothing else, you'd probably predict the mean. So the mean is the naive model. Okay, remember what the mean is? in our example? The mean value of age, I'm sorry, the mean value of blood pressure is 142.53. That's the naive estimate. That is the naive estimate. And what we want to know is, we are going to want to know, is whether the model that we have provides a better estimate than the naive model. Okay? And that would mean that we have an effective model. So, in fact, the fact that the value of t is 4.62, and the fact that we reject the hypothesis at the p less than 0.001 level would suggest that this is an important predictor. Okay, so that this model with age in it seems to be a better model, a far better model than the naive model in predicting y. Now, a better model might exist. That is, it could be that you might have a model that has a curvilinear term, but there's definitely a linear term here. And if there's a curvilinear term, that might provide better fit, but that's something that we have yet to see. Okay, note here that if you don't reject the null hypothesis that beta 1 equals 0, there's one of two things going on. One is that x simply doesn't provide any information about predicting y, so that the slope is really 0. So that's the true state of the world, is that the slope is 0. Or it could mean that the association between x and y looks like this. There truly is a relationship between x and y, and it's a strong relationship. But when we fit a straight line to these data, we fit the wrong model, and we think that the slope is 0. So we have to sort of work on that to see that which one of these two models we're in. Is it that we truly have no association, or it's because we have a strong association, but it's just not a linear one? Now let's consider the intercept. To test the hypothesis that the intercept is equal to 0, we would test this statistic. We would take the calculated intercept minus the null value. And now, again, this null value for the intercept, there's no reason to hypothesize that it was 0 unless you want to see whether the regression line goes through the origin. But otherwise, there's no real reason to test that it's equal to 0. And you divide by the standard error of the intercept, which is equal to this one. Okay, which we again saw. We saw that earlier when I had this slide. This is what I'm talking about here. Here's the variance of the intercept, the variance of the sampling distribution. The intercept, again, I have to estimate sigma squared, and so that's what I have here. Okay. Okay, this estimates that quantity. And this t will be distributed again in t with n minus 2 degrees of freedom. And confidence intervals are constructed in the usual way by taking the intercept plus or minus t times the standard error. Notice that there's n minus 2 degrees of freedom, but all of this is something that we've gone over. So to continue this example, let's say that we want to test the hypothesis that the intercept is equal to 75. Now, where'd that come from? Well, it could be that you were reading the literature and somebody had done this study, same variables, and they found that the intercept in their study was 75. So you say, okay, you tell me it was 75, I believe that. Let's see if that happens in our sample. So in our sample, we found that the intercept was 98.71. So the question is 98.71 significantly different than 75? Okay, so when we plug in 75 into here and we do all the other calculations, we see that the t-value is 2.37. And we reject the hypothesis at the 0.05 level. So we reject the hypothesis because the p-value is something between 2% and 5%. So that would cause rejection. Okay, so we see that it's a very... now, 75 was chosen arbitrarily. I mean, you could have chosen any value for the intercept. It turns out that this tells us that 75 is not a reasonable value for the population intercept, given what we did. And then constructing a confidence interval, again, in the usual way, I've just taken the value of the intercept, 98.71, plus or minus, this is t with the t distribution, and then I'm multiplying t times sy given x and all this. So this is just plugging in that formula. You get the intercept confidence interval is 78.23 to 119.20. Notice that 75 is not contained in that interval. So hypothesizing that the intercept is 75 should be rejected, even if you're looking at that as through a confidence interval. Now, here's the interesting thing. If you give me a value of x, I'll give you back a confidence interval for the mean value of y given x. So this is the last thing we're going to cover for this week, so let's take a short break, and then we'll go into this last topic before we finish the week's work.